Hello, I'm Gabryel Mason-Williams. I'm a research software engineer at the Rosalind Franklin Institute. I'm going to be talking about DisTRaC transient Ceph on RAM. So what I'm going to go over today is the background, so just so that you guys can understand where we're at, what the exact problem is, then what DisTRaC is, how it works, how it then solves the problem, a case study where it worked, conclusion, and then some questions. So the background is that we at the Rosalind Franklin Institute deal with a high-performance compute cluster. And they have four main components, which is a job scheduler, which essentially allocates which jobs go to which compute nodes at different times. We then have the compute, which actually runs all the processing. And these often have an awful lot of RAM that isn't actually used by a lot of the applications that we run, because mainly we're doing it on GPUs. So they don't actually make use of that. We then have a high-performance storage cluster, which often it reads and writes out to, and then we have networking, which is either the interconnect or the storage itself. So that's our setup of our normal HPC cluster. That's the traditional. So what's the problem with that? There are a few. So there are network connection limits to the high-performance file system for I/O-bound applications. We often witness that we have a lot of applications that can write at line rate, and those start to affect other operations that are running on the cluster. Because this is a shared resource, if someone's thrashing that connection, that starts to affect someone else's job that's running as well. Lots of people like to store a lot of intermediate data on these systems, which also starts to cause other issues, especially when it's then later not used. Storage clusters are expensive, hard to maintain and set up, especially when running in the cloud. And we often get a lot of people using these resources completely inefficiently. So HPC is often used by a lot of scientists whose background isn't computer science or efficient programming. It's, I want to get my science done, and I want to get it done as quickly as possible. So what's the solution to this? I say it's DisTRaC. Other people may say other things. So what is DisTRaC? DisTRaC is a distributed transient RAM storage. We specifically use Ceph as the main deployment. And it's a way of deploying Ceph onto a HPC cluster while utilizing the RAM in a scalable and efficient manner. So kind of in short, what we're doing is we're creating a job persistent, isolated in-memory file or object store for HPC applications. So essentially what I'm describing is a deployment tool. So why am I not using current deployment tools? And a lot of them are actually, well, they're built and designed for long-lasting, maintainable clusters that are meant to last for a long time and deal with data for, a good amount and be safe. They're sequential. Often they require passwordless SSH, which is none of the things that you really care about or have access to when you're dealing with HPC applications. And the main thing is that compute should be used for compute and not for setting up storage. We want to be using this resource as efficiently and quickly as possible. So how does DisTRaC work? What's different about it? The main thing here is that we use the parallelization. Since in the HPC setting, everything is heterogeneous and homogeneous, and it's the same. What we do is we create a monitor node. We then place the keys on a shared file system, which then all the nodes can see. We create the manager. We then in parallel deploy the OSD. So this has a constant time. So the time it takes here is the same across all of these. So we don't need to worry about the scaling time. It's efficient. We then create a pool, a gateway, or a file system, and then mount if requested. And then essentially the removal is the same kind of process. We unmount a file system. In parallel, we remove the pool, gateway, and file system. The OSDs again, the manager, the mon. So this is mainly designed for users and scientists. So we try and keep the config as short as possible. So it's simply select your backend, the folder which you're going to write your keys and information to, the interface, the number of hosts, and the service, which is either a gateway, a file system, or a pool. And then you simply state the type of RAM, which is BRD, the number, and then the size in gigabytes. And how it's set up is that you put it inside a job script, set the host names, number of hosts. You then deploy DisTRaC. You copy your data over to your mounted area. You run your heavy I/O application. You then take the data off the cluster, and then you remove the system. So what have we got? We can create a Ceph cluster in a fast and scalable way. We can use DisTRaC within a job submission script. But how does this solve the problem? This solves the problem by now moving the I/O bottleneck to the node interconnect, which is often a higher network rate. It takes the pressure now off the high-performance storage cluster, so we can now make sure that all of our jobs are just operating within a nice wrapped-up environment, which reduces the costs as well in the cloud, because we can essentially get to a point where we don't even need to deploy a high-performance file system anymore. If we have enough RAM and a particular setup, we can just deploy this as and when we need it. And the other additional bonus is that we isolate the resources. So now, if something goes wrong, or there's an error, or there's a system, everything's isolated within those few compute nodes, and we can deal with that. So I'm now going to talk about a case study of an application we use at RFI, which is called Rely On. And essentially, this is a cryomicroscopy technique for determining the structure of biological samples. I don't know loads about it. I'm not one of the scientists. Funnily enough, it's a compute-bound application. However, it produces an insane amount of small intermediate files. And you may say, oh, why don't we just change the code? We don't own the code. This is the stuff the scientists want to run, so we have to run it. And essentially, with this production of tiny intermediate files, it negatively affects our high-performance systems. So we're going to have a look at a setup where we use a data set provided by Cambridge. We have a baseline where we just use the EBS file system provided by AWS. And then we set up the same system where we're utilizing 96 gigabytes of RAM split into 16 gigabyte OSDs, 3 on each host. So the reason why we do that is when you're using RAM, you get a lot from vertical scaling. So what we ended up was a reduction in processing time of 5.1%, total reduction of 4.37%. The total reduction is different because we're taking into account the deployment time. The reduction in I/O overhead was 100% because we could fit the whole data set and the processing inside of the RAM. And this removed the cost and need for running a high-performance file system in the cloud, and it was a more efficient use of the existing hardware. So ongoing work, we're looking to add support for heterogeneous clusters where there are different setups, different amounts of RAM inside each host, and also adding support for on-device drives. So in short, in conclusion, DisTRaC is a deployment tool that creates a hyper-converged HPC cluster for the duration of the job by utilizing the RAM of the compute nodes. It reduces the I/O overhead of the network file system and offers a potential data processing performance increase, and helps better utilize existing hardware to improve the performance of HPC applications. So this project has spanned over many years, so I'd like to just say a quick thank you. Tom Bryan is someone who's here from the FFC user group, and then lots of other people have been involved in the creation of this tool. These are the references, and thank you for listening. Any questions?
Hi. Have you ever thought about there can be two jobs operating on the same data set and they will have race condition as they write out the data? Thank you.
Yeah, so often Rely On and the types of applications we use are allocated to a whole node. So there aren't often multiple jobs running on the same node. So we take it as a, it's only allocated. So we wouldn't have multiple jobs running.
Great, thank you.
Hi, so we have Rely On users, and so we know some of your pain. On the AWS, it said EBS, was that actually EFS?
Yes, it could. No, I'd have to check. It's been a while since I did that test, but yeah.
It doesn't matter. So my more important question is, if you're talking about node-to-node bandwidth, then really it would only really make sense within a sort of MPI island. What we would think of on premises as being a rack. So you couldn't really scale it to 100 nodes or something.
Yeah, no, you couldn't scale necessarily to multiple. It depends, of course, how you've set it up internally within your system, how effective this is as a solution. In the environments we generally have set it up so it's just a rack that we're utilizing on. In the AWS setting, you don't know what you're being chucked on. So we were quite happy to see that we even got a performance increase, was the main note there. But yeah, so there are other things that are kind of hidden away from the user just to say, run this, and it should make things better. It's more of a polyfiller for things like Rely On because of how Rely On is written and similar.
Thanks.
Hopefully an easy one. How many nodes have you scaled this up to?
I think we ran on. In the past I've run on 8 nodes. I think, not much more than that. Generally, I'll process it once we're running at the line rate, and we don't need any more of the RAM. So the jobs are small enough to fit within that.
All right. Oh.
Okay. Just you run a single local Ceph cluster. Do you use another Ceph cluster for just storing data or just reading data from?
Yeah, we use SDFC's Ceph cluster, and different like the data is hosted in lots of different places. We then stream it in for the job.
Okay, and just you mentioned that you have a single Ceph cluster then on the nodes. Have you ever tried to run those in parallel? So two Ceph clusters, for instance, using containerized deployment?
Containers and HPC don't often play very well with each other. Nor it's generally the environment you're set is bare metal, and everyone. If you start talking about those things, people go, no, I'm not interested. So it's the objective is to go as quick and as fast as possible. So yeah, it's a nightmare once you start adding in containers.
Okay, thanks.
Hi, welcome. I'm Lee Sanders. I'm from IBM. I'm based in Hursley, Hampshire. I've been involved in block storage for pretty much the whole of my career. Doing storage development, block systems for about 25, 30 years. I'm relatively new to the Ceph community, last 6 months. Quite excited to be on this project. And so I've been focusing on performance, particularly on block systems for the last 6, 7 years. And I want to talk to you today about my experience being a performance analyst on block storage systems, although the techniques I'm going to be talking about today can easily be applicable to other methods like file and object. Can I show of hands who's heard of CBT in this room? Quite a lot of people, okay. And who's using CBT? I know you are, Jose. Okay, right. So, just to recap, so CBT is a tool that's available in GitHub, freely available for everybody to download. The intention is to have a standardized performance evaluation suite that generates deterministic results. Essentially, you create a YAML that defines a Ceph configuration, and the intention is that automated end-to-end, create your cluster, do your I/O, get a load of results, and then look at the output. So there are sort of like 2 modes. You can automatically get it to create a Ceph configuration for you, or you can define your own, and it will just use your existing configuration. It essentially uses PDSH to log into all your nodes and run all your workloads on all your nodes. It's generally FIO based, although there's no reason why it can't use other tools like VD Bench or other file based IO exercises. And it also allows you to have plugins like it's got a librd support. Essentially, it pulls all the data from all your nodes, and it uses collectl to collect CPU statistics, and which you can then plot. And there's a post-processing tool which is described on the slide to post-process all the data, and it's starting to include Crimson support, which Jose has been deeply involved in improving. So the goal of CBT really is to have a consistent, repeatable method for performance evaluation. At the end of the day, my experience is performance benchmarking analysis requires it's a discipline, right? Quite a disciplined approach. So, which I'll explain later on in the slide about why performance benchmarking as a discipline. So there's quite a number of limitations with the tool. Most of it is to do with post-processing, but essentially we're looking to improve, and I've got a vision which I'll be sharing on CBT later on in the slides. So this is an example output of CBT. We've essentially got it's basically a 4K random writes to 3 RBD images, quite a simple config. But one of the limitations of this output is that it really is only showing you the output from 3 volumes individually. When you're benchmarking your system, you're really interested in the total sum of what it's actually doing, right? And partly because of the post-processing tool, really FIO generates lots of files per volume, and it's really only just plotting each individual file. This is another chart that's generated by CBT, where you can plot IOPS over time. This is with latency, so it's really only showing you the latency of a specific volume, whereas really you kind of want the average latency over multiple volumes. So typically when you're benchmarking your system, you might be running I/O to like 100, 200 volumes. So you can quite easily see that given that you've got 1 to 200 log files, it's a lot of data to try and process. So another thing, which is quite a common mistake in performance benchmarking, is you're interested in bandwidth for large IOs, and you're interested in IOPS for much smaller IOs. But CBT doesn't distinguish that, and it just shows out a bandwidth number. So you have to do some post-processing on the data to break that down into IOPS. Again, that's a limitation of the plot stats tool. So when we're performance benchmarking, what you really want from a user's point of view is how my IOPS affects latency. So what are you familiar with? I know Jose talked about it briefly in his talk, but a response curve. Yeah, a few of you. So when you're plotting a response curve, essentially what this is saying is that as you increase queue depth, IOPS increases, and then you reach a point where you get near the curve, and then latency increases. You can't get any more throughput. So when you're plotting a response curve, you're essentially running I/O for typically somewhere between 3 and 5 minutes at a specific queue depth, and then you plot what the average IOPS was for that particular point, and you keep on doing that, gradually increasing the queue depth, and then you draw a response curve from it. Some people also call this a hockey stick curve, and in some cases, in extreme cases, the curve might bend backwards for various reasons, which I won't explain. So essentially, this response curve is drawing the overall performance, what the application is actually seeing. Right? It's really, really important, and this is one of the disciplined things that you need to take note when you're benchmarking, is the system needs to be put into a steady state in order to draw one of these points, because if the system isn't in a steady state, what can happen is one of these points might be artificially high, and you end up with a line that essentially zigzags or does other weird things. So you have to put it into a steady state. Otherwise, you might get artificially good performance, or in some cases, might not show performance as good enough to sell the system. Other thing is that you're not necessarily interested in the max IOPS or max bandwidth unless you're interested in looking for what the system limits are. So typically, max IOPS and max bandwidth are really only interesting in most cases for marketing, bragging type material, because most customers are really interested in really what am I going to get. Because if you sell a system that can do a 100 gigabytes a second, and then the customer goes and plugs it in, does the first few IOs and doesn't get 100 gigabytes a second, they'll be very disappointed. So that's one of the reasons why putting the system into a steady state is really important. So one of the limitations of the YAML formats for CBT is ordering of tests is not particularly easy. So we're looking to improve the YAML formats to be able to draw these hockey stick type curves. Here's another chart that's quite interesting that uses is that how does latency vary over time? Notes that it's quite spiky, so customers are more interested in consistent performance over spikiness, and where they do get spikes, they really want to know what the worst case latency is going to be. And notes that you can get plotting errors on these kind of graphs because the x-axis along the bottom can mask latency if you don't go fine grained enough. Like if you make this like several minutes, then you can end up masking out some of these peaks and troughs. So the finer grain of this x-axis, the more fine grain you can get the data, and some of that might be tuning the I/O exerciser to plot more down to a second granularity, or maybe minutes, depending on what your requirements are. Here's another chart. So this is where you're plotting a consistent throughput, and some kind of event happens in the middle, like you reset a Ceph node or something like that. And so the customers are interested in what these peaks are, or the worst case latency on the right hand side. And another, of course, along the bottom here, you don't really know what your latency is because it's so close down to zero. So that's another gotcha that you can fall into because you don't really know what this is, so you might have to adjust the graph accordingly. Performance comparisons. Performance evaluation is always going to be some element of variance, typically 5 to 10%. There's a lot of caveats with comparisons. Essentially, performance is only ever going to be comparable if it's run on exactly the same system with the same number of nodes, same number of OSDs, same number of ports, same workload, and even down to the same way you run the tests. So if you pre-filling the system, preconditioning it, randomize the system, and then doing writes and then reads in exactly the same order, that is very important. Otherwise, you're not going to get comparable results. And even so, down to the volume sizes can have an impact, because small volumes can trigger a lot of overwrites, whereas larger volumes, you're a lot less likely to get overwrites. If that makes sense. So volume sizes are very important as well when you're doing deterministic performance evaluation.
Sorry, can you explain that? I didn't follow that about the overwrite.
So say you've got, I'll give you a hypothetical scenario. So 100 volumes, 10 gigabytes each. And if you're doing random block I/O over, say your 100 volumes at 10 gigabytes each, you've essentially got one terabyte of working set that you're doing random I/O over. So the probability of you doing an I/O over that 1 terabyte random is quite slim. Whereas if you're doing a much smaller volumes, then the probability is much greater. If that makes sense, and so you're more likely to get an overwrite than a miss. Yeah. So the vision for CBT, and I don't know what's the time I'm coming up towards the end. So the vision for CBT is that it needs quite a bit of updating to support later versions of Ceph. Like it doesn't include Ceph ADM. We want a tool that does end-to-end 100% automatable, 100% automatable. So you create your cluster, do your I/O, you get the results. We want a process, a procedure where the whole Ceph community can use the same method of doing performance evaluation, so everybody's results in the community are all comparable. We essentially want to generate like 30 plus hockey stick curves, be able to do a regression test in 12 to 14 hours. So some of the erasure coding work which Bill's talking about will require quite a significant amount of performance evaluation, so we need to be able to do regression testing quite quickly. Lastly, we want to be able to generate a full performance report which we can then upload to GitHub repo for the whole community to share performance results so that everyone else can see what the performance is of each other's systems. So that's the vision for CBT, and we'd like everybody to adopt CBT once we've completed all this work.
Do you think we can have a database that every PR that is merged to Ceph, we can run a quick test of performance, and then the next PR we can see if there is a regression, then the PR is blocked?
Yeah.
I know it's, yeah.
I've got a microphone. Yeah. We have discussed that. There's certainly no reason why not. As a part of the report, it will gather all the configuration details, and as a part of that configuration details, there's no reason why you couldn't say, oh yeah, it includes this particular PR and include that in the report. So there's certainly no reason why we couldn't do that.
So similar but different. So 12 hours is a bit long. Probably need lots of compute. Can we think like a smaller set of tests that we can do per PR?
Yeah, we could do that. Yeah.
I was looking into CBT some few weeks ago. I noticed that the latest release was over 7 years ago. It has loads of pull requests. The documentation often refers to Ubuntu 12, Fedora 20. Is it an old project that's being revived, or is it currently reliable for use?
So I've been talking to the original author, is a guy called Mark Nelson at Clyso, and he had openly admitted that he didn't have the time to be able to take it on to do all these improvements, and he was more than happy for me to lead the effort to take all these improvements on. So
it's on its way to be revived.
Yes.
Thank you.
Yeah, we've been doing some epic planning to revive CBT.
And up next we have Mike.
All right. Check. Am I on? Am I on yet? Coming? There we go. How's everybody doing? Oh man, so excited. Oh God, it's gonna be great. All right. So I'm Mike Burkhart. I'm the product manager for NVMe over TCP and VMware integrations for Ceph. I had the luxury of being a VMware guy for 20 plus years, if I can say that. But I'm actually very grateful to be where I am because I have deep roots in the VMware community, but also, I started working with virtualization in general because ESX was booted off of RHEL. It was bootstrapped off of RHEL 3, and I knew Red Hat. So then I was like, well, what the hell is this? and started working with VMware, started getting into virtual data centers, started getting into data center solution architecture. And then on from there, started building large, hybrid clouds, cloud native, et cetera. So working now with Ceph kind of dovetails really nicely with my history in open source community and VMware community. It's a weird 1 foot in, 1 foot out. So show of hands, who uses Ceph? Thank God I'm in the right room. Anyone use VMware? Anyone have VMware in their organization? Yeah, a couple hands, everyone's like, So we're going to go through really quick the integration that IBM has developed for VMware. And it's a plugin that works inside of VMware's vCenter UI that very easily dovetails into the existing APIs and orchestration that Ceph already provides. So you guys already know the top. We've already talked about this today. The bottom part is the really important part. Is the plugin brings the robustness of Ceph into a VMware virtual environment. So my job is not to convince Ceph users to use VMware. My job is to convince the VMware users to use Ceph, right? And I love that. So that's what we're going to be talking about. If anyone has VMware admins that are like, oh God, really, I'd love to use NVMe over TCP. It seems complicated, and I don't really know Ceph ADM or CLI. You're like, okay, forget about it. Don't do that. We got a better solution. So, left-hand side, you guys already know. Clustered Ceph, NVMe over Fabric targets, Rados reactors behind it. The supportability model is going to be software initiators, and this is going to be RHEL or ESXi. Also, we've got SmartNICs, DPUs, Pensando, et cetera, that can basically present NVMe native, and then the hardware is just a direct offload to translate the protocol. And then also bare metal as well. So can do an NVMe initiator or DPUs. So basic high-level architecture there. But what we're talking about is, again, the plugin to vCenter itself. So VMware's UI, and we're going to have SOAP calls between the remote plugin. It's a separate OVA, so it's a self-contained instance. And that's going to, in turn, make REST calls to the Ceph API and do various deployment operations, day 2 operations right now. So the MVP is just a management interface, so deploying new data stores for VMware, expanding, taking care of that life cycle. You'll see too, this is outside of the data path. So NVMe over TCP is going to be brokered directly to your vSphere environment, ESXi. This is a very general, this is the product management slide. So what we saw before was more accurate with the ESXi hosts connecting directly to Ceph clusters. Oh, did I go? Yep, too far. I went way too far. How did that happen? Good Lord, hold on. We're going in the future. Thank you. So first off, I just want to show a real quick workflow. This is just add cluster, IP address, username, password, port number, connect to the gateway service. After that's connected, you can give it a fake ID, FSID alias, and then after that, commit it. The UI itself will in turn create a new right-click menu inside of the UI. It's just that easy. So here, this is just confirmation page. So we've got our alias, we've got alias name, product name is storage Ceph, URL, username and password, and then system is up. We like to see that online. And then you can add multiple systems, multiple Ceph clusters to vSphere environment. And then here, again, if anyone's familiar with this, this is what vSphere client looks like. And this is just your right-click menu. You can right-click, go down to the specific menu you've installed, and then expand, delete, take snapshots, add new storage as necessary. This is a bit of a high-level roadmap, so subject to change. But we kind of started out with, again, we saw data path support for VAI, so that's storage offload commands. So the ESX hypervisor can say, hey, I want to zero this disk out, but it's a heavy operation for the hypervisor. So it just shoves that command to the array, and then in turn, Ceph just zeroes the disks for you. VMware certification, very important to them. Health monitoring, performance, and then currently, later on this year, we're hoping for enhancements, data protection, more integration there. The rest of the stuff, I'm not sure you guys care about, so we'll skip. But we are looking at DR and optimizing monitoring and trending alerting for VMware environment. So, and that is that. That's the easy button. So any questions, concerns, comments? Fantastic. Well, thank you so much for your time. I appreciate you guys. Have a great one.